The name of the presentation is Promise of Mathematica and DoD Operations Research, and I'm William Lewis, the person who's supposed to give it. If anyone's in the wrong place, this is your chance to go. Okay, nobody apparently. So let's kick it off. This is going to be a pretty straightforward presentation, especially compared to my next one, which is across the way in the Illinois room, which is not going to be straightforward. This is essentially a briefing on what operations research on a fairly low level is like in the U.S. Department of Defense. Now, I'm going to be reading a lot of this because I like my own prose. So let's go. Working operations research is a very mixed bag. Academic operations research functions have already been applied wherever they can be applied as vendor supply packages that are programs of record that I can't touch. So most of the academic OR functions are things I never use. They've already been used. Most of the current work that you actually run into is in data acquisition, estimation, including data cleansing and finding out how to hook up to the local computer system, finding the right mathematics to use, and then writing the software. The analyst must be a generalist simply because the set of problems is pretty much undefined. The generalist uses general knowledge to select mathematical approaches that Mathematica then implements. So I remember things that I heard about or read about that ought to apply, look them up in Mathematica, learn how to use the Mathematica functions, and then apply them. In this presentation, we'll give 3 examples of DoD operations research work, and it draws some general conclusions about the usefulness of Mathematica. We're going to talk about 3 grand projects, which will range from not very much use of Mathematica to considerable use of Mathematica. Project number 1, what is the fundamental design objective of service-oriented architecture? What in the world is it supposed to accomplish? Surprisingly enough, almost nobody knows this. No, seriously, you'll see. Second project, can you control a stochastic process that has a non-normal distribution? Six Sigma assumes that it does, that you have a normal distribution, but quite a few processes don't. I'm going to talk about one that has a log normal distribution. Actually, a set of such processes that have a log normal distribution. Okay, and the third is, how can you check voluminous regulations for consistency? In order to do that, you have to locate text that talks about the same thing and then compare text in location A with text in location B. And we'll see how to do that. Again, this relies heavily on Mathematica. Okay. First operations research example, service-oriented architecture. It took about 6 months to do. The question was very simple. What is service-oriented architecture intended to do? And the answer is, as far as I can tell, to avoid the freeze that makes previous software architectures impossible to change or maintain after a decade or two and inoperable shortly after they become impossible to maintain. Although there's a brief interval when the software can't be changed, is known to be wrong, but is still complied with simply as an authoritative source. So if you're looking for AI to take over reality, it happened a long time ago, especially in Social Security. Okay, next question. Is service-oriented architecture needed? And the answer there is yes. We have a generation of corporate research management software, huge things, that's becoming unstable. This software should be replaced by service-oriented architecture. Okay, why? Service-oriented architecture was intended to and actually could implement a market metaphor. And markets persist indefinitely without big ball of mud freeze. In other words, they went from an architecture that has to have big ball of mud freeze to one that historically has been shown not to be subject to that. Now, a big ball of mud freeze refers to the gradual loss of structure under maintenance changes. This gradual loss of structure leaves the software with as little organization as a big ball of mud. hence the name. You can look up big ball of mud in Wikipedia if you want to. That's a very good metaphor. After all structure is lost, after all organization is lost, any change, including bug fixes, introduces more than one bug. So the more you maintain it, the worse you get. At that point, the software is frozen and all changes cease, including maintenance. And it gradually becomes so irrelevant to reality that the workarounds stop working, and then it's completely obsolete and nothing can be done. Okay, question. Can SOA really deliver what it promises? Answer, not in its present form, no. The implementation and introduction was fouled up, I'm afraid, was unsuccessful. Now, in its present form, SOA, Service-Oriented Architecture, SOA, is used to build opaque monolithic systems by engineers and designed to be designed using waterfall methods to be in its final shape from the day it opens, designed by architects and implemented by engineers and understood by nobody else. Big ball of, sorry. Okay, and if that happens, then the big ball of mud freeze is inevitable. However, given a framework and motivated administrators, SOA could implement a market that would resist big ball of mud freeze. In other words, if anyone were actually interested in doing it, then it could be accomplished. We could get away from software that eventually becomes unusable and too expensive to replace. Here's how it works. Service-oriented architecture is intended to support a free market in services and data. In other words, every transaction, if you want data transformed, if you want your data transformed by another node that is selling the transformation service, then you request the service and you actually pay something for it. If you want data, then you pay for that also. There's a contract involved that tells you how much data you can get for each try, how it's going to be formatted, how often you can try per month, the response time, all this good stuff. At least in the classical implementation that isn't typically done. Okay, such a market framework where information and transformation are bought and sold needs frameworks for product definition and for legally enforceable contracts. If someone doesn't pay, you have to be able to enforce it in the courts or enforce it somehow. It also needs a cadre of administrators that are familiar with running such a market. In other words, the administrators have to say, not, gee, the software guys have it, we'll just complain to them. He has to say, we will write a contract through direct negotiations with whoever has the service, if it's something novel, or by looking through their catalog if it's not something novel. Administrators simply aren't used to that and regard it as regarded as well outside their responsibilities. Okay, so a cadre of administrators who would actually do something like that would be necessary for such a market. Neither frameworks nor administrators nor plans to develop either exist. I personally know of no serious development work in this direction, nor, given the generally anti-market mentality of most software companies, is serious development work likely, in my opinion. Okay, in this study, Mathematica was used only to determine the load characteristics of the enterprise service bus, which is the communications means by which services are requested, delivered, contracts are delivered, and so on. The conclusion, SOA can be, okay, and the conclusion there was that SOA could be safely configured as a hierarchical network. It didn't have any pathological distributions that would have choked the network up and made it impossible to work. Okay, questions on this, if any? Go.
Yeah, it seems like you said you're using Mathematica just to determine whether or not there could be bottlenecks in a hierarchical SOA.
Yes.
Which is great, except that hierarchical SOA is a 15 to 20-year-old architectural paradigm that most of the industry has moved to microservices that are REST-based, plug and play, and immutable on top of that. So I'm wondering, you use Mathematica So I guess I'm wondering, is this just a sad reality of government work, or I'm wondering what's going on here?
What's going on is very simple. Okay, first, the analysis was independent of the form of the messages. I was just looking at what happens if you stack SOA systems hierarchically. So let's say you had a national system or a regional system and it went into a global system. How would the second and third orders of the hierarchy react? And again, I didn't find any bottlenecks. Okay, so that's the first one. Second thing is that Marshal Saxe, back I believe in the 1600s, he was the Grand Marshal of France, the Kingdom of France at the time, said that people who do not know what to do will do what they know. And this is what's happened with service-oriented architecture. It's been used to build a system with which the designers and architects are familiar. This is largely because the OASIS and the OMG group did not properly explain the pressing need for SOA and why in the world everyone should have a market. So the people who implemented it were left saying, you know, another bad idea, why should we jump through hoops just because these guys, and besides it'd make a really good hierarchical system, so let's go that way. And they're right, it does help the engineers and the architects, but what it does not do is avoid big ball of mud freeze. Human condition. Okay, so that's one instance of actual operations research work. Okay, so let's try something else. We're going to have to step through this a little bit more quickly. Okay, process control. The trouble with process control is that typically what you're controlling doesn't yield a real number or an integer or anything like that. It yields a range of values. And sometimes the range of values are outside of what the quality control will accept. If that happens, if that's the case, then the question is whether you change the settings on the machine or tell your subordinates to do something else or the equivalent, or you don't. And in practice, if you change every time there's something that isn't accepted by quality control, then you end up what's called chasing the mean, and you can end up almost anywhere if you do that. It's a good way to get into trouble. The problem is largely solved for the case of the normal distribution. One typically uses a chart with a limit and then looks for patterns on excesses of the limit. Okay, but there's very little in terms of non-normal distribution. So the question here is, given a manager, which we had, who had a process that was non-normal, in fact it was log normal, could he possibly control it in some way? So here's a theoretical, very quick overview of a theoretical way of looking at it. Just a second, I'm getting it. There we go. Okay, we'll start with this, a nearly normal log normal. In this one, the peak is just a little bit to the left of the mean. The mean's the vertical gray line. And the thick tail is off to the right. Now, what we find here, just a sec, there we are. Where is that thing? There we are. What we find here is that, okay, have to explain the confidence intervals charts. The purple line on the top is a confidence interval of 90%. In other words, if you draw a sample, there are 9 chances in 10 that it'll be in the purple interval. The purple interval extends from 0 to some natural number. The purple refers to 90%, and the yellow refers to 80%, and the light blue refers to 70%. And by the time you get down to the bottom, you're down to 10%. Any of these things, as far as I could tell, could be used to define a process control chart of the sort that I was discussing before. Therefore, it follows, okay, sorry. So we have three confidence intervals. One goes from 0 to a natural number, one goes from a natural number to infinity, and the other is symmetric about means. Symmetric about means that the probability of drawing the sample that falls into the left part of the purple line, with the boundary being the horizontal line that goes up almost, with the boundary being the vertical line. The probability of falling into the left-hand interval is equal to the probability of falling into the right-hand interval. In other words, the symmetry has to do with probabilities rather than with length of the interval, okay? Okay, any of these could be used to control the process. You just draw boundaries and then look at the dots that go out beyond the boundaries. If you get five or six of them in a row, then you know something's badly wrong because that's hugely improbable. It would be, seeing a pattern like that is the equivalent of 0.1 to the sixth. That's the probability of it actually occurring. So this can be managed. Now let's go down some and look at this second, also log normal. Here alpha is 1 and beta is 0.3, whereas above alpha was 1 and beta was 0.1. Okay, and in this interval you can see that the hump, the peak, is is even more skewed to the left, even more displaced to the left, and that the long tail is even more pronounced and it goes off to the right. Notice also, okay, now in the confidence intervals, the one saying 0 to double n, notice that the starting point for the top one is a little further to the right than it was before. In other words, before it was a 3 point something and now it's almost up to 4. Okay, by the same token, the natural number to infinity confidence intervals are all a little bit more to the left. This means that the band in which you cannot easily detect changes is much larger, or somewhat larger than it was before. Your control has become a little bit less certain. Okay, the symmetric about the mean, you'll notice there that there is no purple line. That's because there is no symmetric confidence interval with a probability of 0.9 of dropping into the interval. We've completely lost the ability to check symmetric, to check whether it fits into whether samples fit into a symmetric confidence interval for any probability below 0.88. Okay, so what we're seeing is a degradation of possible control. Now, you can control this process, but not as closely as you'd like to. Okay, region 3 is very, very strange. It's almost counterintuitive. Just a second. Come on, guys. Okay. Region 3 is just about counterintuitive. We're looking at a log normal distribution with alpha 3 and beta 3.6 here. The mean of this, instead of being 3 or 5 or 6 the way you think it is 13,000. Way over to the right. The tail is very, very small. The tail goes out a very long way. And in this one, we lose yet more. Here are the same confidence intervals that we've been looking at before. If you have to have symmetric control of the process, you only get a confidence interval of 7%, completely useless. If you're looking at 90% confidence interval, you can only control that everything within 2,000 has to be accepted. Below 2,000, again, your control of the process has gotten very much worse. Okay, now what's the problem? What's the problem here? Why in the world did I put this up here? The answer is that The answer is that it's first to show it's the versatility and necessity of Mathematica, and second, is to show that the usual response to this, which is to say you have to make 90% of your deliveries on time, or else you'll face an investigation, is completely ineffective. Okay, now almost done. Okay, this third one, I'll say very, very quickly. We had a heck of a lot of regulations to look over, and the problem was to check it for consistency. In order to do that, you have to find two chapters, two text divisions that refer to the same subject, and then compare them to see whether they actually say the same thing or say something that contradicts each other. The problem is finding these. What we did here was to look, okay, all acronyms in DoD have about the same syntax. So we could locate acronyms, which we did, and here we are. Just a sec. Okay. The hash numbers here refer to different chapters. It's just a hash of the chapter title. The similarity refers to how many acronyms it has in common. In this case, the bottom two pairs had no acronyms in common, and the top pair did. So for that reason, we would inspect the top and not the bottom. Now, after applying it to everything, we end up with the histogram that looks like this for similarities. You'll notice on the left it starts at 0 and it goes on up to the right. 1.0 means that the two sets of acronyms are identical, and presumably the two chapters are talking about the same sort of thing. Now, in practice, if you start at 0.2 in similarity and only look at chapters that have a similarity of that or greater, then you've probably gotten all the chapters that might contradict each other. You don't have to look at the chapters that have nothing to do with each other. And in practice, you can get, you can eliminate 97.9% of all the chapters. And what's left, just to show you how much is saved, at the third hour, 20 minutes per comparison, taking care of these 5,821 chapters would take about 300 work days of labor, which is one of the reasons why it's never done, and the contradictions, if there are any, remain in place. Okay, so one more slide and we are done. Have about a minute to do it. Okay, many fields require generalists. Generalists introduce hypotheses, and you can see that we had quite a bunch of hypotheses there. What SOA is supposed to do, that was basically a literature search. Can you control a log normal process? That was mathematics and exploratory mathematics. Can you find a way to eliminate some vast bulk of work? That was text processing. Now, Mathematica is about the only language I know of, it is the only language I know of, that can provide adequate support for support for such a diverse set of undertakings. So Wolfram language in this respect is a cognitive enhancer, and we're done.